Okay. Here. Hopefully we're live at the moment. Check to make sure. Yeah, good. Check my analytics to make sure healthy. Okay. So today we're gonna go over day 3 real quick. We kind of read through this before. So we're gonna go basically column by column, count the zeros and the ones. If there's more zeros, then if it's more zeros or more ones, the more one goes to the gamma. And if there's less, it goes to the okay, the epsilon rate is calculated with the use of the rather than use least common. So we're going to try to do that real quick. Okay. We're going to do that in Python. Day 3. We're going to do sample. Okay, there's our numbers. And we're going to do a for x in range 32. First let's do for value in that, right? And for in range of 32. What we want to do is we want to see, and we also need a value estimation right here. We're going to need a count equals 0. And we're going to need an array. So we're going to need bit count. Going to equal, is it just like 32 times 0, right? Is that how we do this? We'll have to see. And basically what we're going to say, if value ended with 0x1 shifted over by x equals that mask of kind of like this individual bit mask, then we're going to say bit count. Well, we should call this one count, right? We're really counting the ones. One count of x plus equals 1. And then we're going to print one count. Oh, we also need to do count. Do that here. Count plus plus equals 1. Okay, and then we need to process this. So we're gonna have so we're gonna need a gamma equals 0 or epsilon equals 0, right? Now we're just going to do the 432 again. But this time, what we're going to say, if 1, yeah, divided by 2. Yeah, if one count of x is greater than count divided by 2, that would mean the 1 is higher. So the 1 would go to epsilon. So what we need to do, or the gamma gets that 1. So what we need to do is we need to say gamma equals gamma ORed with 0, 1 over x. Else else it's epsilon. And then we just want to print gamma and epsilon. That. $22. That don't seem right. 'Let's put the hex in front of this one as well. Seems like a weird issue. Oh, yeah, okay. So we want to say if one count is greater than 0 first. One count is greater than 0. We don't know how big the size is. Okay, so let's get rid of that. 22 and 9, is that correct? 9 and 22. We'll use the most common bit, multiplying the gamma together. Okay, now we're just going to multiply them. 198. Okay, I guess we could process the bigger one. But let's get the HLS core going and we can process the bigger one. So we need to go and create a day 3. New folder, day 3. Folder, HLS. Let's go to day 2. Copy the source folder over here. Ugh. Wish it was smarter and would know what I meant, but oh well. But now let's get some. Right. Let's go look at how the PYNQ. I want to look at the PYNQ real quick. PYNQ. Right here. That. PYNQ. How does the PYNQ do its HLS on the right here when we go to the pixel pack 2, right? Might be in the color convert too. Are they doing any fun okay, yeah, you can just go like that to do beginning and end bit. Okay, so we could do that if we wanted to. Or just do a single one. Okay, let's grab HLS and get another one going. So let's go file, new project. Okay. Browse, because you never know where to go. Day 3, HLS, select folder. Say day 2, day 3, part 1. No, just call it project, right? Day 3, part 1. We can add files. That's the correct folder. Those files there. Don't worry about the function. Add files. Test bench. I think that's good. And then we'll just select the board. DCU 104. Finish. Okay, let's go to our source. We have our input stream, and we're going to have a gamma S. How can I never spell that? Epsilon, 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 epsilon. So before we're gonna do the same thing, right? We're gonna have a count, and yes, we'll do 32 of those. That's 8. 16. Okay, cool. We'll have something at the class where it just uploads. This is where it's just going to update these. How would we do it, right? We need to create a value, so I think we'll just have to create a temp value for these. Call it what? Temp and etemp. Okay, that's about it. We'll have to do the calculation. We'll probably can put those even inside here. Temp equals etemp. So we're gonna basically do the calculation again. So for int index equals 0 and index is less than 32, index plus plus. What we're going to do is we're going to go through these values, and we're just going to say if temp.data index equals 1, we're going to say inputs. No, this is one count. Let's do one count. One count of index. We're going to plus equals 1. Do I have to give this a name? How do I think I have to give that a Vitis HLS name for loop. That's a nice little system. How do I name the for loop? Do I just put a name in front of it? I don't remember how to name for loops in HLS. Vitis HLS. Oh, yeah, great ones. Data flow, channels, there, FIFOs. Does he have like a name? Okay, we just gotta give it a loop name, right? We do that. We have that right there. Booyah. We're gonna do a complete unrolling of it. And we just wanna say count plus equals 1. And then we'll need to create a kind. Yeah, we want to refresh the count right here. Count equals 0. And then we want to do we want to do another for loop here. Call this the end loop. But we're going to say if this value is greater than 0, right? And if not that value, but one count of index. One count of index is greater than 0. One count is greater than count divided by 2. And we're basically going to say gtemp of index equals 1. This is kind of the binary operation. And etemp. Did I close it? Okay. I think that's good. So let us emphasis on it and see if it's happy with it. Did I change the name? A3 part 1, refresh the inputs, but we're going to call this gamma epsilon. Okay. Did we get the synthesis? And then let's get the data, the sample data, which is 12. Window. What do we have? Oh. What do I have to do? Can I just say? I think I'm gonna have to reset it all the way. Let's do it. Clean up loop, and we're just gonna say uncount equals 0. Solution. Okay, you have this error right here. So you don't like how I'm indexing it. Do you need a range? I can give you a range. What if we do like index x? Solution. Active solution. Oh, gamma epsilon. Okay, I think we've cleared up our issues and we should have something soon. I'm gonna see what the latency is and then I'm gonna do some magic. Okay, I mean it looks all good. Yeah, it looks good. Well, let's try Mr. Test Bench, right? I don't think we kept this line. Run C simulation. Oh, we forgot to add the last. The last is important in this situation. Uh, um, if I equals 11, temp that last equals 1. This is important in this situation because we operate differently on the end of the data than we do at the beginning. G did not update. Interest. Did that not? Right. So gamma. So I guess we're gonna print printf, right? Loop. We're gonna do a %d backslash n. Yes. Say index, and this will be tell us if one magically went forward or not. Relation. See, that's a little concerning, right? We shouldn't be seeing ones that high. Um, First input is a 4. We should only see this on percent. No, let's go 0x percent 0.8 big X. Um, why are the inputs acting so? This is annoying. Oh yeah, yeah. Why is the data not going in correctly? Seems concerning. Oh, um, why not? I want to see how it acts to that terminology. Um, right. What's happening to our values here? Let us put in a 4. Change anything? Oh, well, it will. Let's try. What is happening with then? Why is my data all over the place? It's really weird. I literally assigned a 4, and I expect to see a 4 afterwards. Why is there no 4? Oh, cool. F max is very high value. Um, I am kind of stumped here. Why is our 4? Yeah, that's what we should expect. Why is the data so wrong? What if we take this out, right? And put temp data back here. Three, four, 1, 2, 3, 4. I'm gonna assign it all F's. Does it not? Yeah, the value is not changing. Oh, that doesn't make sense. I'm about to throw my hat in and call it a night because. Oh, are you saying just because you just want me to assign things? No, not there. Here. Is it because of this? Is it because the nulls inside of this are making it go crazy? I mean, I could see that. Maybe it just wasn't realized at first, but like it's reading the wrong memory address. Maybe I'm simply printing it out wrong. Try that, I guess. Standard. Why? They're saying my printf is not working. So is it just my printf? The way I tried to do my printf was not working. Anyway. So I guess that works fine. But yeah, it's still not what's going on with data? Is it being corrupted there? Parameter function. Why is it not calling the function? Okay. This is going crazier. It's getting even worse. So let's go here and see what it comes up with. Oh, I don't know what's going on here, guys. Oh, okay. That would be a big issue. What's the value supposed to have? 22 and 19. Um, oh, now we want to do inputs I. Wonder if that was just breaking it. Okay, cool. That was oh, crazy. Sheesh. Finally. So let's just go ahead and active solution. So the big issue is I wasn't reading it after I was creating it. Rally's on you. Um, Lindsay. Let's. Okay, yeah, seems fine. Bunch of ads. Okay. Yeah, let us export RTL. Output location will be folder. The export. Vendor AEW day 3.0.0 day 3 part 1. So let's get this building. File, save as it was 3, and then I'll drop this 4 into there. So get rid of part of the HLS cores. IP catalog. Guess we'll just remove that project. Okay. Source. Correct. Add repository. A3 HLS. Double click. Add to design. Connection automation. I don't really feel like doing part 2 tonight. I think after that, terrible. Terrible issue. Validate. Okay, validation successful. Generate the bit stream. And I will go play with this. Let's go ahead and just go input. Cool. So now we're going to do function. Cool. Now if we register that, do 3. It's way slower. Yeah. Right, because this one was that good. Or no, that's slow. Edit, copy cells, edit. Do that here. Useless. That's okay. J3. HLS. May. Buffer. Fill buffer. Do transaction values and right. Okay, cool. Now we're just waiting for their bit file. Okay, while that's running, let's go ahead and just submit this day value. So continue the part 2. Next, you should verify the life support rating, which can be determined by multiplying the oxygen rating by the CU scrubbing rating. Both the oxygen rating and rating are values that can be found in your diagnostic report. Find them in the is the tricky part. Both values are located using a similar process that involves filtering out values until one remains. Before searching for either rating value, start with the full list of binaries from your diagnostic to adjust the first bit of these numbers. Then keep only numbers selected by the bit for the type of rating value which you're searching. Discard numbers match the bit criteria. If you have one number left, stop. This is the rating value for which you are searching. Otherwise, repeat the process, considering the next bit to the right. Ooh, we're gonna have to. Guess we'll have to. Value. Bit in it. Okay, this is a little bit more the long criteria. Okay. We'll have to play through that one another day. But as soon as this is done, we can demonstrate the performance difference. But yes, we can try to read through. Okay. Start with 12 numbers. There are more 1 bits than 0 bits. So keep only the 7 numbers with a 1 in the first position. Oh, that is a pain. Then consider the second bit of the 7 remaining numbers that are more 0 than 1 bits. So keep only the 4 numbers with a 0 in the second position. Oh, in the third position, fourth position, in the fifth position, there are an equal number of 0 bits and 1 bits on it. To find keep the number with a 1 in the position. Whoa, this is a weird one for HLS. I don't know how to go about this. It's like gotta flip the values. But if we're expecting to stream it, we might not be able to do that. We might just have to list. I have to think about this, find a good way to do this. That could be a hard one. Do random access memory. You don't know the next thing until you read all of them. What would be a smart way to do that type of computation in HLS? Also, we have to determine the bit width. We might have to make that a setting. Maybe we can do multiple iterations. I'm just trying to think of how you would do that type of problem in HLS. How you would break that apart. Way. I mean, the easiest solution I think is just you just send the DMA the times the bits, or just let it have random access where it stores the information. That wouldn't make much sense. So I mean, I was trying to think of it. We send the data back to ourselves, where it gives a list. I'll have to think about this one. So it's just kind of a tricky one to think about. Oh, I was curious. Let's if we go back to the HLS, right? Down here it says 137 max. I wonder if we could play around with the settings to get this to go faster. Huh. Good way. There. Maybe looking at the utilization breakdown. Um, okay, almost done routing. You almost want to create a tree here. That's what I'm thinking, right? We're creating a tree. We have a tree of zeros and ones. Then those have zeros and ones, and then those have zeros and ones. We need to create a tree. Yeah. If we create a tree, we can figure out the answer. We want to generate a tree and then follow the paths at the end. How do we create a tree? Well, we know the bit width, we know the tree, so we just need to create a tree structure. We'll have to do a fixed memory for the largest width. Or we could just aim it to basically want a 32 by 32 by 32 by 32. That work? How big of a memory space are we talking about here? A tree, not too big. What do we two? Two. Yeah, we could do a tree. We could do a tree. A tree would probably be the best way to proceed down this path. We're going to create a tree while we do this, and then grab it. I probably won't create a tree in Python. I'm probably going to do the naive approach of copying it, and then we can try to do a tree in HLS. Generate a tree, but the issue of the HLS is going to be a fixed tree. And let's look at your puzzle input where this A3 is. It's 12 bits wide. We probably want to do fixed 12 bits wide. So I mean, in the end, we're going to be looking at a really funky tree. You're writing the bit stream. Let's go ahead and get day 3 going here. Directory day 3. I'm gonna go rename day 3. Runs station Working on that bit file. Okay, it's done. Rename day. Drop it. The day 2 automatically. Nope. Good. So let's go see how much faster we can do it with this file. Load that. Oh, it's. I played that. There we go. Register map. Okay. DMA. This DMA. Transfer it. Oh, there we go. $199,389. What was that delay? Okay. Okay, so this took 4 there. So almost 200x improvement. So we only have a almost have a 200x improvement part 2. So we almost have a 200x improvement for this calculations. I have to figure out how I'm going to create the tree. I guess we want to do it in Python, do a Python tree, and then do a hardware tree, and see how it is. I think, I wonder how that. Okay, so that's good. We got it working. Figure out what we want to do for part 2. We'll look at that tomorrow. Maybe I'll see if I can continue this. We may look at something else tomorrow, like ETH hash, but I'll figure it out. Thanks for enjoying the video. We're going to continue doing all the advent of code. I'm not sure if I can keep this pace. They seem to get harder and harder and harder, but we'll eventually do it. What's 25? The sea cucumber. Ah! We'll have to encode that. That'll be fun. Whee! Okay, so